Bismillah ar-Rahman ar-Rahim. Welcome to this lecture, which is number 3 for optimization processes on methods for optimization. Today, we are going to make a review. This review is about using derivatives to find maxima and minima. So today we have some review. Using derivatives to find maxima and minimum. Okay. We'll do this through two different examples. The first example is that we have a cardboard and this cardboard has a rectangular shape. And we need to make a box from this cardboard. We need to make a box. Okay, so this cardboard has those dimensions. Let's see. Okay, the whole dimension from here up to here is 21, and the dimension is also from here to here is 16. So this is the cardboard. We have here, we take from this a small rectangle with a dimension of x, and here x, and here also this one is x, and this one is x. So we take those rectangular pieces from those four corners to make this box. So the box, when you bend those edges up, you will have a rectangular shape. So the rectangular shape will look like this. Okay? The rectangular shape will be like so the rectangular shape will look like this. When you bend this side here, this one will be x. Notice that if you take x from this side and x from this side, then you have 21 minus 2x. And so this dimension here is 21 minus 2x. And the dimension also here is 16 minus 2x. So what we are looking for is to maximize the volume. Okay, find the size. So the statement that we have here is we need to find the size of the corner square, which will produce a box having the largest possible volume. Okay, so when you bend those sides up from this side and from this side here, you will end up with this box. The amplitude of this box is x. The length here is 21 minus 2x, and the width here is 16 minus 2x. So the sizes of the volume will be the length, the width, and the amplitude. Three of them multiplied by each other. This is the volume. So we can formulate a volume using those in terms of those square the corners at the square of each of this cardboard. Sorry. Okay, so let's do this. Now, the problem is clear. You have a cardboard, you are going to take squares from them to make a box. Those squares, we need to play with those squares and look for what size of x, what should be x, such that this volume of the box is maximum. Okay, we'll let everything in terms of x and try to make it as a minimization, or sorry, the maximization problem. All right. So we need to maximize V, the volume, which is equals to x times 16 minus 2x times 21 minus 2x. So this is my volume here, the volume of the box that will be produced. Okay, but we have one constraint. The constraint that we have is that this x here cannot be, and the x here, they cannot exceed 8. Notice that if you have x to be 8, then it's 16 minus 16, there you end up with 0. So you don't have to have an x that is large like this and another x that is large like this, and they end up getting the whole side to be more than 16. So twice of x should be less than 16, or 1x should be less than 8. So our x should have the constraint such that x is greater than or equal 0, less than or equal 8. And actually, I will take this equality so that it's forbidden to have 0x. If x is 0, then you don't have an amplitude if x is 0. And if x is more than 8, then you don't have a width. So x should be between 0 and 8. Okay, so this is our problem, and this is the formula that we have. Let's multiply it and find V to be equals 2 times 168x minus 37x squared plus 2x cubed. So we multiplied those two together. 3 of them, we took the 2 as a common factor, and we end up with this third order polynomial in x. Okay, to get the largest possible value, then largest means that we need the maximum. Maximum means that we have to differentiate, find the critical points, make sure that we find the second derivative then, and you make sure that you have a negative sign when you apply the critical point at the second order derivative. Okay, so I'm going to take dv by dx, and this is equals to 2 times 168 minus 74x plus 6x squared. So this is the derivative. Let's take also another 2. So this is equals 4 times 3x squared minus 37 plus 84. And we will let this equals to 0. To find this is to find the possible critical point. To solve this, we have x1 and 2 equals to, you have a, b, and c, so this is plus 37 plus minus the square root of 37 squared minus 4 times 3 times 84 divided by 2 times 3. So if you calculate this, then this is 37 plus or minus 19 divided by 6. So x1 is equal to 18 over 6, and this is equals to 3, and x2 is equal to 56 divided by 6, and this is equals to 28 over 3, which is more than, so x2 exceeds the constraint. So x2 exceeds the constraint, so this one will not count, and we have x1 is our only critical point. So we have 2 critical points. One of them does not apply to our problem, and we have x equals 3. So this is what we are looking for, and we would like to make sure that this is a maximum. How to make sure that this is a maximum? We will find d2v by dx squared, which is equal to, find the function here, d2v, so it's 2 times the derivative of 168 is 0 minus 74 plus 12x, and this one should be applied at x equals 3. So when we apply the critical point on the second derivative, we end up with a value of minus 76. So this is less than 0, which means that v is maximum at x equals 3. So our x is, that will maximize the volume of the box is x equals 3. Notice that if you take the lower bound 0 for x equals 0, so you will have v equals 0. So for x equals 0, v equals 0 times those 2 factors, and at the end v equals 0. If you take x equals 8, then v is also 8. 2 times 8, 16. 16 minus 16 is 0. So this one is also 0. If you take x in between, which is equals 3, which should be a maximum, then you will have v equals to x, which is 3, times 16 minus 2 times 3, 6, 10 times 21 minus 6 is 15. So 15 times 10, 150 times 3, it's 450. So our maximum volume for x equals 3 is 450. So this is the maximum value that we will get for x equals 3. So this is one example on how we usually find the minimum or the maximum. Now we are looking for the maximum, and the first derivative gives us, when you differentiate and find the first derivative, you find the critical points by equating the first derivative equal to 0. Find the second derivative and make sure that the value evaluating the second derivative at the critical point has a negative value. If you have a negative value, then this is a maximum. If you have a positive, then this is a minimum. Actually, what we are looking for, if you have a negative, this means that your curve is concave downwards. And if the derivative is positive, then the curve is concave upward. So this one here belongs to such a curve. This one here belongs to a curve with dv by dt, or the second derivative is a positive value. Okay? All right, so let's move to another example and see also how we're gonna see if we need to minimize what will happen in this case. All right. Okay, in example number 2, we have a wire of 60 centimeter long. This wire need to be cut, so you have a wire of 60 and we need to cut it somewhere. So the wire should be cut somewhere, and we will cut the wire, and we will let this piece here to be x. So this x should make a circle. So the prime meter of this circle is equal to x, which is part of this 60. What is left here, which is the amount of 60 minus x, should be transformed into equilateral triangle. This one is a circle. So we will take a piece of this 60 centimeter, make a circle, and we'll take what is left from the 60 centimeters, and we'll make an equilateral with equal sides. So this side equal to this side equal to this side. And this one here is circle with prime meter of this, the circumference. Circumference of the circle is equal to x, and this is equals to 2 pi r, where r is the radius. So r is the radius, and it is equal to x. 2 pi r is equal to x. Okay? 3s here, 3s is equal to 60 minus x. So the three sides of the equilateral triangle is equal to 60 minus x. Okay, what we are looking for Okay. Okay, this is the statement. Where should the wire be cut in order that the sum of the areas of the circle and triangle is a maximum B a minimum. Okay, so we'll see both cases. Okay, I hope that the problem is understood. You have a piece of wire, its length of 60 centimeters. We need to cut it somewhere. The first part we'll call it X. The next part we'll call it 60 minus X. The first part we will make from the first part a circle that has a circumference of X, which is equal to pi r. The next part, which is 60 minus X, we make an equilateral, مثلث متساوي الأضلاع, equilateral triangle with this prime meter. So the prime meter of this triangle is equal to prime meter of this triangle is equal to 60 minus X. Okay. All right. Then the area, so this is what we are looking for, to make the sum of the areas. So let's do this in terms of X. We will try to find the area of this circle, the area of this triangle, add them together, and try to make either to differentiate to find the critical point, find where is the maximum, and find where is the minimum. Okay, we will start doing this. So the area of the circle, and let's call it AC, it's equal to pi r squared. Okay, now there is a relationship between r and x. R here is equal to x over 2 pi. So our r, the radius of the circle, is equal to x over 2 pi. If you plug it in this equation, then the area of the circle is equal to pi r squared, and this is equals to pi times x over 2 pi squared, and this one is equal 1 over 4 pi times x squared. So this is our first relation. Okay? Okay, the area of the triangle. The area of the triangle is AT, which is equal to, okay, we have this as the base of the triangle, which is equal to S, and we have this to be the amplitude, or the amplitude of the triangle. This one here is, notice that this is an equilateral triangle. This means that this one is 60 degrees. This one is also 60 degrees. And this one also is 60 degrees. So the length here, this length here is S sine 60, which is equal to square root of 3 divided by 2 times S. So the area is 1/2 times the base, which is equal to S, times the amplitude here, which is equal to square root of 3 divided by 2s. So this is equals to square root of 3 divided by 4s squared. Okay. What is s? S here, in terms of x, is equal to 60 minus x divided by 3. If you put it here, so this will be square root of 3 divided by 4 multiplied by 60 minus x divided by 3 squared. And 80 is equal to square root of 3 divided by 36 multiplied by 60 minus x, the whole thing squared. All right. So the total area A total is equal to AC plus A of the triangle. And this is equals to 1 over 4 pi x squared plus square root of 3 over 36 times 60 minus x, the whole thing squared. So this is the our formula for the total area. Okay. Now I'm gonna differentiate the A total by the x, which is equal to 1 over 2 pi x minus square root of 3 over 18, 60 minus x. Okay, please do the differentiation. The differentiation of this one is 2x, so the 4 with 2 they will be cancelled with each other. The differentiation of this one is 60 minus x squared, then the 2 will come here, 60 minus x times the differentiation of the one inside, which is minus 1. So this is why you have a minus sign here. Okay? Okay, so if we let this to be equal to 0, okay, then we have only 1x, and this x, take those as common factors, and you end up with x to be equal to 10 square root of 3 divided by 3 over 1 over 2 pi plus square root of 3 over 18. And this is approximately equal to 22.61 centimeter. So if we go to the wire again, so you have to have from those 60 centimeters, so this one is 22.61 centimeter, and this one here is 60 minus 22.61 centimeters. Okay? Okay. Is this a maximum or a minimum? Notice that you have only one critical point. One critical point, which is 22.61. Now, if you take the second derivative, d2 A total by dx squared, this is equals to 1 over 2 pi. So I'll take the first derivative, which is here, 1 over 2 pi, okay? And this one here is plus square root of 3 divided by 36 times 60 okay, I'm sorry, just to fix this one. 1 over 2 pi plus the differentiation of this one is plus square root of 3 divided by 18. Okay? And this is definitely is greater than 0. This is always positive. So x equals to 22.61 yields a minimum value for or of A total. So the total area will be minimum at this value 22.61, and A will be approximately 1 over 4 pi times 22.61 squared plus square root of 3 divided by 36 times 60 minus 22.61 squared, and this is almost A total. A total is almost equal 107.94. The total area is 107.94 square centimeter. Okay, so this is the minimum. Where will the maximum happen? The maximum, we have actually the edges of the periods. Notice that your x here will be greater than 0, less than 60 centimeters. So if those are the edges of the interval, so our maximum will happen at one of those values. And if x equals 60 centimeter, it means that the whole thing will go into a circle. Then all the wire will be used for a circle. And A total equals AC equals 1 over 4 pi times 60 squared, and this is 268.48 square centimeter. Okay. If x equals 0 centimeter, then all the wire will be used for triangle, and A total is equal to A triangle, which is equal to square root of 3 divided by 36 times 60 squared, and this is equals 173.21 square centimeter. So we'll have our maximum. This is our maximum. We get the maximum if x, the whole thing, or the whole wire is used as a circle. and the maximum value is this. Actually, if we, just to make a small draw, if we take this axis to be x, and here is a total AT and AC, and we'll take each one of those to be in different color. Let me just say that, okay, AT in green and AC in red, then we will have, sorry, AC in red to start from 0, and we end up with a maximum of 268.48 at this point here. So from x equals 0 up to x equals 60 centimeters. So this is x. This is the curve. If we take on the opposite, if we take the green, which is the triangle, then it will start from somewhere here, 173.21, and it goes down like this. So it will go down like this. The blue color is their summation. So this is the triangular curve of area as a function of x. This one in red is the AC, the circle area, and their addition will be something like this. It will start from this point, going down like this, and it goes up like this. And you have the minimum somewhere here at 22.61 centimeters. And this minimum here is 107.94. So this is the curve, the green curve for the triangular area, the red curve for the circle area, and the blue curve is their addition. It goes from, it swings from 173 until 268, but goes to a minimum at x equals 22.61 with a value of 107.94. I hope that with this we have a flavor of how to do problems for optimization and how we formulate the problems. We will see next if we have more than one variable. If you have like x1 and x2 and x3, then what should we do for the derivatives? And what should we do for the second derivative? In first derivative, we will have what is called the gradient of the variables. And the second derivative, we will see something called the Hessian or the Hessian matrix of the parameters that we have. Okay, looking forward to see you in next lecture. Thank you very much, and I hope you will enjoy it. Thank you.